also called limited pressure cycle, or mixed cycle. So in this cycle, we have five processes, out of which two are isentropic, two are isochoric, and one isobaric. Now, isentropic process is also called a reversible adiabatic process. Isochoric process is also called reversible constant volume process. And isobaric process is also called reversible constant pressure process. Now, process 1 to 2 is isentropic compression, just like in case of Otto and diesel cycles. Process 2 to 3 is constant volume heat addition. Process 3 to 4 is constant pressure heat addition. Process 4 to 5 is isentropic expansion. And process 5 to 1 is constant volume heat rejection. So these are the five processes that we have. Now, let me draw the PV and TS diagrams in this case. PV and TS diagram. Process 1 to 2 is isentropic compression. So in the TS diagram, we will get a vertical line pointing upwards. Whereas in the PV diagram, isentropic compression is represented by a curve like this. So here, as we are considering compression, the pressure increases and volume decreases. And as the pressure is increasing, temperature rises. Then process 2 to 3 is constant volume heat addition. So constant volume heat addition is represented in the TS diagram like this. So here the temperature is increasing when volume is kept constant, and as the temperature increases, pressure also increases. So we will get a vertical line in the PV diagram. And 3 to 4 constant pressure heat addition. So that is represented in the TS diagram like this. And in the PV diagram, constant pressure heat addition is represented as a horizontal line, as we know that when pressure is kept constant, temperature is directly proportional to volume. So that's why as the temperature increases, volume also increases. Then 4 to 5 is isentropic expansion. So isentropic expansion is represented like this. So during expansion, the pressure decreases and volume increases, and temperature also decreases due to expansion. Then 5 to 1 is constant volume heat rejection, which is represented on the TS diagram like this. And here 5 to 1 is constant volume heat rejection, which is represented as a vertical line. Now these two are obeying PV power gamma equal to constant. Now here we need to come across some ratios. The first one is compression ratio. Compression ratio is denoted by R suffix C, which is volume at the beginning of compression by volume at the end of compression. So V1 by V2. Volume at the beginning of compression is V1 and at the end of compression is V2. So compression ratio is V1 by V2. So here we will come across cutoff ratio. So this cutoff ratio is denoted by rho, which is volume at the end of heat addition, which is V4, by volume at the beginning of heat addition, which is V2. As we know that V2 is equal to V3, we can write V4 by V3 also as cutoff ratio. Then here we will come across one more ratio called explosion or pressure ratio. So this is denoted by beta, which is the maximum pressure to the pressure after compression. So P3 by P2, or you can also consider it as P4 by P2 as the explosion or pressure ratio. Then coming to expansion ratio, expansion ratio is denoted by R suffix E, which is volume at the end of expansion V5 by volume at the beginning of expansion is V4. So we know that V5 is equal to V1 because 5 to 1 is constant volume process. So we can write V1 by V4. So if I multiply and divide by V2, we can write like this. And we know that V1 by V2 is compression ratio and V2 by V4 is 1 by rho. So we can write expansion ratio as compression ratio by cutoff ratio. So this is very important term that we need to remember. Now heat supply. So here in this particular cycle, heat supplied is taking place in two different processes. One is during constant volume, the other one is during constant pressure. So during constant volume process, heat addition is mCV delta T. So mCV T3 minus T2 plus during constant pressure heat addition is mCP T4 minus T3. Now heat rejected is during process 5 to 1, and as 5 to 1 is constant volume process, we can write mCV T5 minus T1 as the heat rejected. Then work done is heat supplied minus heat rejected. We can write this as mCV T3 minus T2 plus mCP T4 minus T3 minus mCV T5 minus T1. Then coming to thermal efficiency. Thermal efficiency is work done by heat supply. We can also write this as 1 minus heat rejected by heat supplied because work done is heat supplied minus heat rejected. So 1 minus mCV T5 minus T1 divided by mCV T3 minus T2 plus mCP T4 minus T3. We can write. So this can also be written as 1 minus T5 minus T1 divided by T3 minus T2 plus gamma into T4 minus T3. So we know that Cp by Cv is gamma, which is ratio of specific heats or adiabatic index. So this is the formula for thermal efficiency in terms of temperatures. Now let us get this thermal efficiency in terms of the ratios that we have seen. Now, in order to get that, we need to get all the temperatures in terms of T1. So for that, let us take process 1 to 2. Process 1 to 2 is isentropic compression, so PV power gamma equal to constant. We know that the relation between temperature and volume in case of isentropic compression is T2 by T1 is equal to V1 by V2 whole power gamma minus 1. So V1 by V2 is nothing but RC to the power gamma minus 1. So from this we can write T2 is equal to T1 into RC power gamma minus 1. So let us keep it like this. Now let us go for process 2 to 3. Process 2 to 3 is constant volume process, and during constant volume process we know that temperature is directly proportional to pressure. So from that we can write T3 by T2 is equal to P3 by P2. P3 by P2 is nothing but beta, which is the explosion ratio. So from this we can write T3 is equal to T2 into beta, which can also be written as T1 RC power gamma minus 1 into beta, because T2 is T1 RC power gamma minus 1. So we got T3 in terms of T1. Now let us take process 3 to 4. Process 3 to 4 is constant pressure process. Now, when pressure is kept constant, temperature is directly proportional to volume. So T4 by T3 is equal to V4 by V3, which is nothing but rho. So from this, T4 is equal to T3 into rho, which can also be written as T1 RC power gamma minus 1 into beta into rho. So this is the formula for T4. Now let us take process 4 to 5. Process 4 to 5 is isentropic expansion. So PV power gamma equal to constant. We can write T5 by T4 is equal to V4 by V5 whole to the power gamma minus 1. So V4 by V5 is nothing but rho by RC, as we have seen previously. So rho by RC to the power gamma minus 1 we can write. So from this, T5 is equal to T4 into rho power gamma minus 1 by RC power gamma minus 1. We know that T4 is T1 RC power gamma minus 1 into beta into rho power gamma minus 1 by RC power gamma minus 1. So these two will get cancelled. We can write T1 into beta into rho power 1 plus gamma minus 1. So here we will have rho power 1, a power m into a power n, a power m plus n. So these two will get cancelled, and T5 can be written as T1 into beta into rho power gamma. So we have got all the temperatures in terms of T1 and the ratios. Now we know the formula for thermal efficiency in terms of temperatures, that is 1 minus T5 minus T1 divided by T3 minus T2 plus gamma into T4 minus T3. Let us substitute the values here. 1 minus T5 is T1 into beta into rho power gamma minus T1 divided by T3 is T1 into RC power gamma minus 1 into beta minus T2 is T1 RC power gamma minus 1 plus gamma is here. T4 can be written as T1 RC power gamma minus 1 into beta into T3 is T1 RC power gamma minus 1 into beta. So in the numerator, let us take T1 common. So then this becomes beta into rho power gamma minus 1. C power gamma minus 1 common in all the terms. So this becomes beta minus 1 plus gamma, and here in these two terms let us take beta also common. So gamma beta into rho minus 1 we will get. So T1 gets cancelled, and finally we can write thermal efficiency as 1 minus 1 by RC power gamma minus 1 into beta into rho power gamma minus 1 by beta minus 1 plus gamma beta into rho minus 1. So this is the formula for thermal efficiency of a dual cycle. So we need to remember this particular